So hi everyone, welcome to this new LLM seminar. Today we have Debasish from Southampton talking about this ergodicity-breaking scenarios in quantum link lattice gauge theory. So let's welcome.
Thanks, Jay, and thanks to all of you for the thanks to Zlatko for the invitation, and it's a pleasure to be here. So I will talk about these ergodic breaking scenarios in quantum linked lattice gauge theory. The topic, the ergodic breaking scenarios is something you're experts in. So I'll tell you a bit about how our work in these scenarios as regards to lattice gauge theories, what results we have. So I'll discuss two main scenarios of ergodicity breaking. The seminar is, like we don't have to go through all the slides. You just make sure, we are comfortable with what I tell you. So this work was mostly done with me, Arnab, and the younger collaborators, Indrajit. He's currently a postdoc in ICTS, and Shaptoshi was a master student from ISER Kolkata, and now he's a PhD student in the US. Right? And we'll talk about, so the two scenarios that we had in mind are the context of quantum stars, which we looked at in the, again, pure lattice gauge theory, quantum ring lattice gauge theory. I'll tell you what it is. And the other is the standard notion of MBL and how ergodicity breaking happens through MBL when you put disorder in the system and you. So this is a very something recent. Just after a long discourse with the referee extending for like 1 year, it finally got published a few weeks back. Anyway, so it's a bit. So if it's okay, I'll go to the slideshow because yeah, that's why I'll do it. It's, yeah, now it's yeah. So I think the introduction is kind of redundant here because all of you are more experts on this topic than I am. So for example, we are interested in quantum systems with many degrees of freedom, whether be it from the condensed matter point of view or high energy point of view. And we know that things thermalize, but how fast the thermalization is the question. Can you evade it? So we had a nice discussion about this member effect, which I learned today about how you can make it slow or fast. Can you evade this? And traditionally, there have been the way of evading thermalization has been the paradigm of Anderson localization or many body localization, where you put disorder in the system. You make the couplings random, such that whatever disturbance you make, the disturbance does not propagate in the entire system. And this has given rise to notions of what people call weak ergodicity breaking and strong ergodicity breaking. And I'll talk and I'll touch on those topics. And of course, it's relevant to emphasize that there's been a lot of theoretical progress which is driven hand in hand with experimental progress that's being made not only with quantum simulators but also quantum computers. Right? So we have many of the things that we can try and test around. So these figures, I think you are all familiar with. This is the trapped ion simulator. This is an optical lattice simulator, and this is a cartoon of a quark-gluon plasma. So, for example, in the LHC, you have hadrons, right, which are colorless, and these colorless objects are being collided, and what they give rise is to a medium where color is not confined inside these molecules, but rather become a property of the medium, right? That's why this medium is colored, is colored, and this is what we call quark-gluon plasma. So in the context of high energy physics experiments, we know that things thermalize, right? We want to understand how, again, the rates of thermalization, is it fast, slow? I think it's not very easy to ask these questions in a collider experiment because everything is just so out of equilibrium, and it's very difficult to separate out the quantum effects that one has a much more control over quantum effects in quantum simulators or quantum computers rather than in a collider experiment where you're banging everything. But that's also why I think a lot of the high energy physics community is also interested in developing these quantum simulator and computing tools where you can engineer these states and have a precise control on entanglement, and you see how these things evolve. Right. So the way of thinking evolution or thermalization in quantum systems proceeds by this Eigenstate Thermalization Hypothesis, because as we know, quantum mechanics is really a unitary evolution. So you can always recover the initial state if you know the final state in all its details, right? You can do a reverse time evolution and you can find out initial state. So what really happens is that you can start from an initial state, which is which is like a product state. It doesn't have many correlations. But as the system evolves in time, the initial correlations are delocalized. In some sense, the entanglement grows. So if I look at this small patch of of this, the subsystem, you have this big system and you have a small subsystem, and you're looking at the subsystem. So initially it may look decorrelated, but finally it gets correlated as the quantum system evolves, right? And this entire approach is understood by this eigenstate thermalization hypothesis. And of course, so that's all nice. But what is more interesting is the fact that there are new, increasing examples of translationally invariant interacting systems coming up, which show different kinds of ergodicity breaking. So you have quantum many-body scarring, you have fragmentation, and so on. And this has caused quite a lot of excitement in the community, right? Yeah. So the usual way of thinking about ergodicity is that you have an operator. You're looking at the time evolution of the operator, and you sandwich this within the time evolving Ketz and Bra, and then you expand this out. So you have a term which is independent of time. Right? This is the infinite time limit. And this is what will ultimately become the microcanonical ensemble. But then you have an interference term. And this interference term depends upon, has a phase which is Em minus En, which is the difference of the eigenstates and the matrix element OMn. And the standard understanding is from, as far as I understand it, is that, of course, when you have a many-body system and you're looking at high energy states, Em and En are exponentially close by because you are fitting in an exponential number of states in a gap, which is scales with the volume. So Em and En are exponentially close. So therefore, ideally, to go to the microcanonical ensemble, your T would have to be exponentially long. But this is not what happens. We always typically observe thermalization happening in order 1 time. And that's also, of course, because this OMN has the off-diagonal element, which is suppressed by the exponential of the entropy of this. So therefore, this off-diagonal element washes out, goes to 0 much faster than what one would otherwise expect. All right. So these, I think, are well-known ideas. So how does one typically think of ergodicity and its breaking? So one nice way of looking at ergodicity is the fact that you take a computational basis, and you have this basis, and you make a state space, right? You count all the possible bases, which I label as a point over here, and then the Hamiltonian can be thought of as connecting the different dots, right? Connecting the different points. So this is sort of a Fock graph representation of the Hamiltonian, if you wish. And typically, most of the interacting many-body systems we are familiar with have one fragment, right? One fragment, they are ergodic in the sense that if you start from one particular point, any of these Fock states, and you start applying the Hamiltonian will make sure that, after successive applications, you reach all points of the graph, right? The graph is connected, so to say. That's the ergodic part of it. But of course, this need not be the case. There are, so the more examples that are coming up are examples where things are fragmented. So here, for example, I have a system with, it's a 6-pin system, so I think it should have 2 to the power 6 states, but it's a constrained system, so it only has 18 states. And somehow the Hamiltonian is such that it does not connect all these states even. It has different sectors, right? It has, so there are different fragments. And based on how, what kind of fragments you have, there are one classifies them as weak breaking and strong breaking. So the weak breaking has, again, how I understand it is that it has many anomalous high energy states. So you can, whereas and it breaks ergodicity in a weak fashion, right? But of course you can make this quantitative, whereas a strong fragmentation breaks ergodicity strongly. It has exponentially many fragments, and you can build in this, you can introduce this notion that, let me define this ratio, small n divided by n dot. So small n is the Hilbert space size of the biggest fragment, and capital N dot is the the total Hilbert space of this entire system. And you ask the question that how do this ratio on the left-hand side scales as you increase the system size, right? So if it turns out that the scaling goes as exponential of minus L, in other words, there you as you take the thermodynamic limit, you have exponentially many fragments, but no one fragment is important. So this is an example of strong fragmentation. On the other hand, if you have scars, we say that in the thermodynamic limit, they all thermalize. That's to say that the biggest fragment, which is ET satisfying fragment, would essentially go to the ratio of that with the total dimensionality of the Hilbert space would go to 1 as your volume goes to infinity. So therefore, they would still thermalize in the thermodynamic limit, even though at low times you might have interesting athermal behavior. So that's yeah. Right. So now enter gauge theories. So of course, whatever I said before does not assume any particular theory in particular. This says that you have an interacting many-body theory. Now, gauge theories are a subset of all the interacting theories you can have. But what is interesting about them is that most of the fundamental theories of nature, like quantum electrodynamics or quantum chromodynamics, use a gauge theory description at the microscopic level, right? So I mentioned quantum chromodynamics here, but of course, there's also the example of quantum spin ice. I'll come to it in a moment. So quantum chromodynamics starts with, comes with its own oddities, right? Electrodynamics is its own, is a more simple theory. You have electrons and you have photons, and whatever states you put in your microscopic theory are the states you observe in a scattering experiment. Those are the states you can realize. But quantum chromodynamics is more special in the sense that whatever degrees of freedom you are putting in your microscopic Hamiltonian or action are not the states you observe in real life. So they are not the states you observe at low energies, right? So you start with these degrees of freedom called quarks, which are fermions, and they're interacting with each other through gluons, but you don't observe isolated quarks or isolated gluons in the spectra. Instead, what happens is that there's a phenomenon of confinement, and that makes bound states. Right? These bound states are either baryons, so 3 quarks, or mesons, quark and antiquark. So traditionally, this has been what has been observed, but recently, in the past few years, people have also reported candidates which are tetraquarks and pentaquarks. So bound states formed of 4 quarks and 5 quarks. They're exotic objects. They are things that cannot be explained by the traditional bag model of confinement. So there's a lot of interesting activity from lattice QCD as well, trying to keep such states as stable and or so on. But that's not the only part, right? So there is a lot of gauge theory that is used in condensed matter. So one has frustrated magnetism. So that's one of the standard playgrounds where you have so many so classically you have many ground states and you have an emergent gauge theory description. But I would like to focus a bit more on quantum spin ice. So quantum spin ice, you have these pyrochlore materials with this tetrahedral structure, and whether you have and the arrangement of the positive and the negative ions are such that one can think of these tiny magnetic moments, right, sitting on the vertices of a tetrahedra, and this actually at zero temperature, all of them want to be in the state of lowest energy, but you'll soon realize that they are frustrated. So in the sense that there's not one ground state which is allowed, but rather several for one given unit cell. And when you replicate this unit cell in the entire volume, you very soon have an exponentially large number of ground states, right? Classical ground states. But now at zero temperature, if you want to tunnel from one classical ground state to the other, you soon give rise to loop operators. And these loop operators are exactly the kind of operators I will be talking about. So they are the plaquettes of the Hamiltonian. So what's also been interesting is that these models are not particularly new, right? So, and they have been investigated both from particle physics and condensed matter side. So the people in blue that you see, so these models were, the first historical evidence we have is in 1981, was studied by David Horn, and then Peter Orlan and Röhrlich in 1990s, and then finally Uwe and Shailesh, they kind of discovered these models completely independently. I mean, all these works are independent works, right? in 97, and since then there has been a push for using this model for QCD. Well, not since then, but they wanted to use these models to simulate QCD because they could write down better classical algorithms for it. But at the same time, they were very much unaware that in condensed matter community, people were using the standard Rock-Sharp-Peterson models to model the non-nil state of high temperature superconductor, right? And also people were also studying various magnetic theories with these models. So these parallel things kept on existing until I think around 2012 or 2013. That's when we realized that these models are actually the same thing. The Hamiltonians are the same. It's just the Gauss law sectors are different. And that's also when we started talking to mathematics a lot. And I think this helped us in trying to understand the physics of these models. Right. So I will tell you a bit about what how these models look like. Of course, many of you already know this. So instead of so the traditional lattice gauge theory starts by thinking of a quantum rotor that sits on an even length. So that's the way Kogut-Susskind thought about it. But let me not go into that direction. I'll directly go to quantum links. So the way when you think about quantum links is that quantum link models is that every link, right, every link that connects two bonds, you put quantum spins over there, right? And quantum spins already have a finite dimensional Hilbert space, so it's 2s plus 1. And quantum spins have three components, right? And s plus s minus z. And it turns out that you can identify the z component with electric flux, and the gauge fields can be identified as the raising and the lowering operators of the electric flux, right? This particular identification allows you to write down these commutation relations. EU gives the commutation of U, EU dagger is U dagger. This is all there in the definition of the spin operators themselves. And it turns out that the first two commutation relations are exactly the ones that the Kogut-Susskind Hamiltonian also has. So in a sense, what happens is that you are writing down the same Hamiltonian as Kogut and Susskind did or Wilson did when they wrote down the lattice gauge theory. The only difference is that the degrees of freedom are different. So in the standard Wilsonian lattice gauge theory, the degrees of freedom are quantum rotors. In the case of quantum link model, the degrees of freedom are quantum spins. At the level of the abelian gauge theory, this is pretty simple. At the level of non-abelian gauge theory, this is, again, formally it's the same. It's just the operators are a bit more complex with more indices hanging around. Right? So that's all. There it is. So what you have in addition, so there are a couple of things different. So first thing, the first thing that is different is the fact that U and U dagger, because it's a finite representation, no longer right? So you this 2D. So this means that the ground state physics need not be the same as the Wilsonian theory. That's the because you have a different theory. And another way of thinking about it is to imagine that when you are taking your continuum theories and you're putting them on the lattice, right? There are two levels of regularization you're doing. So first is the fact that your space-time is continuous. You're putting it on a lattice, so you're this is what typically one does when one does renormalization. Right? You are making everything on a finite lattice such that your momentum integrals don't go to infinity anymore. Right? You have a finite cutoff, and that cutoff can be thought of as 1 by A. That's the very standard thing. Standard regularization. That's what is done in lattice gauge theory all the time. The second regularization corresponds to the fact that when you are dealing with bosons as opposed to fermions, your Hilbert space is infinite dimensional with bosons, right? So this is not so harmonious if you want to do, for example, quantum computers, because or quantum simulation, because you have a few states which are under control, and you want to truncate or map the theory, the infinite dimensional theory, into a few quantum states which you have a good control on. So quantum link models are more natural in that respect because the spin representation gives you an action parameter. For each value of spin representation, you have a completely gauged invariant. Right? So the notion of truncation does not enter like that. All you're saying is that there's an extra parameter in the theory which you can change, and this parameter can be half, 1, 3 halves. And in fact, analytically, it can be shown that if you take s to infinity, just by using coherent state approach, you can write down a path integral an action which looks very similar to the Wilsonian theory. Right? And you can recover the Wilsonian limit if you take S goes S and E. So that's a very clear, clear way to proceed. Yeah, and of course, feel free to interrupt me anytime. Right? So I'm going to work with spin half representation, and this is the simplest way to think about. I mean, this is simplest conceptually easy. So every time you have an arrow, right? If an arrow is going to the right, I think of this as plus half flux. If it's going to the left, it's negative half flux. And of course, you cannot raise a flux which is already plus half. So this is annihilated. You cannot lower a flux which is already negative half. So this is also annihilated. The Hamiltonians, what we are going to talk about, look like this, right? So again, remember that when you are thinking for a gauge theory, right? The gauge theory Hamiltonians have two parts. One is the square of an electric flux, one is the square of a magnetic flux. So E squared plus B squared, right? This is how you do it. Now, immediately you see that there's an E term, right? I've identified SZ with E. So if I have to write the electric flux squared, I would have written an E squared term over here, right? Straightforward. I would have written the term definitely, but it turns out that if you're working in spin half representation, your SZ squared is a constant because SZ is just a Pauli Z, and that's a constant. So we don't write this term. This doesn't add anything. If you're doing spin 1, spin 3 halves and whatnot, one should definitely add the term. That has a very relevant effect on the low energy physics, right? So instead so therefore you can neglect the electric squared E squared term, and you can only think about the B squared term, right? And the B squared term turns out to be this. I think I have a longer explanation about this. So the B squared term is the following, can I use the board for 1 minute if I can? Yeah. So in the standard Wilsonian theory, what happens is that U is thought of as e to the power I lattice spacing times A mu, where A is a vector potential. So trust me when I say that if you take a plaquette and you do this calculation U dagger, and the Hermitian conjugate, you are going to get a term which looks like cosine A times B, where B is a magnetic field, right? So that's just saying that if your lattice spacing was going to 0, A goes to 0 limit, you would, the leading order term would be a B squared, because, when you expand the cosine, we are not taking the A tending to 0 limit, right? You're strictly non-perturbative. So the full plaquette term that we have is what I call this U box, which is like a U dagger. And this is a closed loop, right? So this goes from X to Y, Y to Z, W to Z to W, and W to X. So I'll tell you what these operators are. We will look at this. So the Hamiltonians we will have is like, so the first term, the opening term, is a magnetic field term. So this would give rise to the B squared term in the continuum limit, right? Now, having a Hamiltonian with only Okin is a bit boring because it's just nothing really happens. It's a confined theory, and that's the end of it. But it turns out that if you add this extra term, which is which we call potential, and again it'll become clear why am I calling it potential. So this potential term is just the square of the individual plaquette, right? So you take so if you wish, it's like a B squared and B to the 4 term, right? So it's a square of the plaquette, and then you sum over all the plaquettes. So this is something I will call the potential energy term. It will become clear in the next slide. So the Hamiltonian, therefore, is Okin plus lambda times O potential.
What is U box?
Yeah.
So product of the U's?
It's the product of the U's.
Right. Go ahead.
Yes. Right. So let's now understand what is being done by this U box, right? So Okin is just, right. So Okin, remember, is just the sum of U box and U box dagger, right? So what is this U box? U box is U dagger, and U has been identified with S plus, right? So this is a raising, lowering. The dagger would just be the opposite, lowering, raising, right? So you have a force-spin interaction, and these force-spin interactions can act on these plaquettes, right? Since you're working with spin half representation, right? So there are 2 states per link, right? So in a given plaquette, you would have 2 to the 4, 16 possible states that it can act on. But however, notice that it's very important that the polarization of the states are in a particular are ordered. So you have an S equal to plus half, minus half, minus half. this state, if you act on it by the Okin, it can be lowered, this can be lowered, this can be raised, and this can be raised. So you go from plus half, minus half, minus half, to a minus half, plus half, plus half. So this is an effect. So you can think of the magnetic field energy, right? Or what is the operator doing is that if it identifies a closed loop of a half flux, right, in the anti-clockwise direction, it flips it to a clockwise direction, and vice versa. Right? If it finds a clockwise direction of flux, it makes it an anti-clockwise direction. And already notice how constrained the system is, right? Because of the specific ordering, S plus, S plus, S minus, S minus, out of the 16 possible states that you can write down on this plaquette, it's only 2 which are non-zero, right? Only 2 of diagonal elements exist. The rest are all zero. So it's a highly constrained system. So it's, it's not like a spin model sometimes, where you can flip all of them, but you cannot flip most of them. So the action of O king is just to flip. What is the action of O potential? So the O potential, if you go back, if I go, if I go back one slide, the action of O potential was to square the U box, right? So essentially, O pot can be thought of as doing the flipping it twice, right? So this just means that if you start with the around the plaquette flux, which is in the anti-clockwise fashion, right? You will first flip it once, it becomes clockwise, you flip it back again, it becomes anti-clockwise, right? So it's a counting term in that sense. It's just a term which you would like in your Fermi-Hubbard model, it would be just a term that it's a density interaction. It gives you a well-defined value. It just counts how many how many of them are flippable. So in this case, that's exactly what O potential does. Moreover, O potential can only count plaquettes which are flippable, right? It cannot count the 14 states which are not. So it can only count clockwise or anti-clockwise. Of course, if you wish, you can add a chirality term by saying that if it is flippable clockwise, I'll give +1. If it's flippable anti-clockwise, -1. These are interesting things to play with. But these are the two most obvious terms you can write down in an RG inspired group, right? I mean, I write down the E squared plus B squared. E squared doesn't enter. So you write the next possible term according to RG. This would be B to the 4. So that's what you come up with, right? So right, so you already see that this model is constrained, is highly constrained, and it turns out that you can even write down a local invariance, right? So of course this is a model of electrodynamics. So you have this usual Gauss law operator that you can write down, which is again the same as the divergence of E, right? I've just only discretized the divergence on a square lattice. So it's just all the fluxes that go out from X to X plus I minus the fluxes that come in from X minus I to X. So it's literally the lattice divergence. I don't have any fermionic rho X term over here because I'm not considering fermions, right? Fermions are not dynamic. It's just, if at all, if they're present, they will be present as static objects. And I'll explain how the static objects come. So the existence of this operator means that the Hamiltonian commutes with the Gauss law. And this is the global symmetry of the system. The Hilbert space splits into different superselection sectors, and each of these sectors can be labeled by that local operator Gx. Right? So typically, from because we were coming from a particle physics point of view, right? We always had put Q equal to 0. We said that all charges should be 0. And in this, so with this particular model, this selects for you 6 possible states. Exactly. So 2 in, 2 out rule. And this, this maps somehow to the quantum spin ice problem that I was telling you. But anyway, it's on a different lattice. It's on a square lattice and not on the parallel. So you end up having 6 states, and this is what we had studied before. But we then became aware that if you can also choose your Gauss law sector, and the necessity of the choice comes because sometimes in studies of confinement, what we want to do is that we want to violate the Gauss law at one point by putting a static charge, and another point by putting an anti-charge, and compute the static potential between them. And what we do is that so of course, the location of the charge and the distance between them gives a distance, right? And you can compute the potential as a function of distance. And then what happens is that the potential is rising, you conclude that the theory is confined. But of course, if it doesn't rise forever and the string breaks, right, the potential flattens out, this is a very clear case of string breaking. That's what had inspired the initial studies of string breaking. And in this model, you can put charges as well. So you can put a charge q equal to 1 by making sure that so in q equal to 0, notice that whatever flux was coming in was going out, right? So here, 2 of them are coming in and 2 of them are going out. That gives us the six configurations. For q equal to 1, you have to make sure that 1 comes in and 3 goes out, such that the divergence of E gives you a +1 over here. So if you look at, this first realization, you see that, one of these fluxes comes in, but 3 of them go out, right? So, and you can do this in 4 possible ways. So the way to realize q equal to 1 would be to have 4 states, right? Similarly, my -1 will also have 4 states. Q equal to 2 is the maximal possible charge you can realize, because q equal to 2 means that all fluxes are going out. And you cannot put bigger charges than that in this model. To have bigger charges, you'd have to increase the spin representation. Then you can put in bigger charges, right? So a lot of control is there when you're constructing the model. Right? So as I said, for the quantum link model, it's a bit of a misnomer, because quantum link models refer to the entire class of models that one has. But since this was the first time, first one we were studying, we call them quantum link model. So the Gauss law sector of this model is 0, right? You say that all states are annihilated by this operator, this divergence of E that one has. Right. And the thing that I will not talk about, it's not relevant for our purposes, is that in addition to the various point group symmetries, translation, rotation, reflection, you have these continuous symmetries, which are the winding number symmetry, right? So these refer to how many times a flux loop can wind around on the torus, and they're characterized by integers wx and wy. I will not refer to them. In all the results that we have, I will show you, we have always put this to be 0 under 0. We always look in the maximal winding number sector. So there's no flux winding around the system. So what is the connection with the diamond models, right? So quantum diamond models have played sort of a pedagogical role in condensed matter physics for a very long time. So it turns out that, and the quantum diamond model is the fact that how, you have this electronic system, and the electrons form singlets with the nearest neighbor, right? It doesn't have to only form a singlet with the nearest neighbor. There are long range models as well. But the simplest model that Rockshire and Wilson had was the model of, nearest neighbor singlets, right? And the diamond model is such that if an electron forms a singlet with, this neighbor, it cannot form a singlet with anything else. So therefore, no two dimers can touch a side. So it's like, every side is a single dimer. So this is what the diamond model looks like. And so at some point we realized that if you take the quantum link model, the same Hamiltonian, but you say that I'm not interested in the G psi equal to 0 sector, but instead in this sector, right? It's -1 to the power x1 plus x2. So you can think of it as a staggered charge. You can think of, I've taken the same configuration. All I have done is that I have now mapped the dimers. So the presence and the absence of the dimers is related with a number 0 and 1. You map the dimer occupation with the electric flux, right? Just by this relation. And right, and then you compute the Gauss law, which is the divergence of E. And you see that at every dimer, so this entire model maps to a theory of staggered charges. It is as if, you are in this point, you see that there are 1, 2, 3 fluxes coming in and 1 going out. That's a negative charge. And for the red point, you have 3 fluxes going out and 1 coming in. So that's a positive charge. And this is all there in a staggered fashion. So any configuration you have for the diamond model, you can map it to a configuration using links and background charges. So that's how we realized that these two models are really the same. Right?
What is that, the ground state of your Hamiltonian?
It's just the Fock state.
Just the state.
Just the
Fock state. That's
right.
right.
Right. And you can show that the Hamiltonian maps all Fock, the entire Fock state maps to itself. So you can, using this, you take a lattice, you count all Fock states, and you can show mapping holds. Right. Okay. So, so as I told you already that these models have these point group symmetries. They have an internal symmetry, discrete internal symmetry, which is charge conjugation. which means that U goes to U dagger goes to U, and E goes to minus E. And it turns out at lambda equal to 0, you can define this particular operator, which is a product of the electric fluxes, along these lines, and this anti-commutes with the Hamiltonian, right? And this, of course, implies that given an eigenstate E, you have a charge conjugate or chiral partner with energy minus E, and as has been studied by index theorem, by also by Zlatko here, that all these these statements imply that you have the density of states has a peak at 0 energy, and this is a number of 0 modes, right? So you have so I'm just showing you the density of states on two systems, on a 10 cross 2 ladder and a 6 cross 4 system, and you see very clearly the peak, the delta, the peak at equal to 0, right? And of course, the symmetry is very, the distribution is very symmetric. And this is just a reference to what we were talking yesterday, Zlatko, is that you also see these tiny peaks over here, you see symmetrically. These are that, this is exactly the one +2 and -2 over here. And that's what, made us go suspicious, and we were trying to play this theory of this long range thing. But anyway, I'll skip to that. But these are not so prominent. What is prominent is that the E equal to 0. So we started looking for signs of, well, the entire project that started a long time back was to see whether confinement, what effect confinement has on dynamics, and that's a question it needs more discussion. But at least in the entire endeavor, we managed to find out non-thermalizing, or let's say anomalous thermalizing states. Right? So these models are non-integrable, and they are strongly interacting. There's no easy non-interacting limit of the models, right? And in all the results that I'm going to show you, we have looked at excited state physics, and this entire the numerical machinery comes from using exact large scale full ED. So you really diagonalize the system, and at regions where you need, you cannot diagonalize the system entirely, you either use Langshaw's, but Langshaw's doesn't work so well with high energies, in which case you use shift invert. This is also a well-known technique, and this is just to give you an estimate of the sizes. So with Langshaw's, you can easily go up to 64 spins in quantum link models, 96 in quantum diamond model. This large number is simply because you have a Gauss law as a constraint. So this doesn't let the number of states still rise exponentially, but it's less than what you would have in a spin model, right? With full ED, you cannot go much beyond 48 spins in a QLM so remember, the quantum link model has 6 states per side. Quantum diamond model has 4 states per side, which means that the Hilbert space of quantum link models is larger than the diamond model, right? So this is 48 spins, and at 48 spins, the Hamiltonian is almost like 50,000 to 100,000, right? So, and that's the limit of what we could do on our clusters. So because we were studying delocalization and there were some objections to the by the referee, we had to do this shift invert to go further from 48 to 56 spins in the QLM. And yeah, this is not something which we could diagonalize fully. So this is 616,227 Hilbert space. So this is where we used a shift invert, right? Right. So how do we know that these models are non-integrable? So what we looked at is this plain and simple level spacing distribution, computed by this. I think you're all aware of this, and this would have been the usual Poisson line if it was integrable. This is the GOE, and you see that for reasonable values of lambda, right? For lambda equal to 0, -0.5, -1, all of them are close to GOE. Right? So they follow. So this is a really non-integrable limit of these systems. If you make lambda very large and negative, this distribution does shift to Poisson. This is just a statement, because then the plaquettes cannot flip that much, so it does start going there. Right? Okay. So how does this scarring occur? So I'll try to motivate this a little bit already. So remember, I showed you that the Hamiltonians we had this form. We had this O-kin and O-pot, But you can imagine this as, some operator T, which is of diagonal in your computational basis. So our computational basis is electric flux basis. It's something, your electric flux is plus half minus half. It's physically very intuitive. So that's what the computational basis is. So this was Okin in the computational basis. And then you had this O potential. So you can have any generic operator, right? You can write down this generic Hamiltonian. And mostly what you will have is that T and O, they do not commute with each other. This is what we typically have. Now, as we saw at lambda equal to 0, if you remove this O object, right, then you have your OK. This operator T has a zero mode subspace and a non-zero mode subspace. Don't worry about the relative sizes. They are not the. So you have some zero modes and non-zero modes. And this is exactly the point. And at lambda equal to 0, the zero modes are protected by an index here. Now, when you switch on a lambda at finite, some sort of coupling, these zero modes and the non-zero modes start interacting. Right? Just because you have your Hamiltonian is no longer separated into T and O, but rather lambda connects them. And certain states within the zero modes, which were previously embedded in the zero mode, start becoming very prominent. And this is what we see as quantum scars. And so this is what we have. So we have this, the T has a continuous spectrum. When I say continuous, I just mean that you have, like bunch of eigenstates which are exactly zero, and then the rest of the spectrum has no specific number. Right? It's just a real number. Whereas the other operator O has a point spectrum, as in it counts the number. So in our example, the O potential counts the number of plateaus. So it will always have an integer valued, it's a discrete spectrum in that sense. So when you start coupling them, then it turns out that a certain number, and this number can be either order 1, or proportional to the volume, some power of volume, or exponential in the volume. Some of these zero modes, they also end up diagonalizing the operator O. So it turns out that we realize scars as special eigenstates, which are simultaneous eigenstates of both the T and the O operator. So they are not commuting with each other, right? It's a many-body system. You kind of start making states which are simultaneous eigenstates of two non-commuting operators, and therefore they are anomalous. They are not generic eigenstates of the Hamiltonian. They're very special eigenstates of the Hamiltonian. So they're anomalous already by this argument. And so these special modes, they violate the ETH. In addition, we also see some non-zero modes. It's not a model. The non-zero modes, anomalous zero modes also come up. So this is the mechanism. I'll just explain this thing better by what comes up. Yeah. So how long? When should I stop?
Within the hour, if possible.
Yeah. Okay. Good. Right. So the anomalous states, what we look at is as follows. So we have, so you look at the von Neumann entanglement entropy as a function of the energy density for ladders, right? Where Ly is kept to 2 and you increase Lx, right? Between 8, 10, 12. And you see that you have the usual ETH satisfying band, with the entanglement entropy values going up. But then you have some special states where the entanglement entropy does not scale, right? This is almost fixed. You see the same thing in some correlation function as well. So this EJ is really the correlation function of the electric fluxes, right? Along the y direction. So you also see these anomalous states in the correlation function. So that's where we first observed it. And these states are such that they are simultaneous eigenstates of both the kinetic and the potential operator. So in the sense that if you act Okin on these special QMBS quantum many-body scars, they annihilate the state. Whereas if you act the O potential on this QMBS, you get an integer number, right? And this means that all the participating states, right? So this is an eigenstate. So all the Fox states, you can decompose this to have the same number of livable plateaus, right? And what I'm showing you on this figure is just the amplitude of one of these quantum many-body states at different values of lambda, right? So these states never change. Once you've constructed such a state at a given lambda, so these states, will be there. So they will move in the spectrum very deterministically.
How
In some-
many of these states are there?
Pardon?
How many are?
Yeah, I'm coming to that. They are exponential in the linear dimension. So yeah. So in our first paper, we only found 4 because we were looking at some chains, but then the thing started becoming clearer what was going on. So this was the quantum link model. The quantum diamond model also has exactly same phenomena. So your Hilbert space, in the Fock space, you have this localization. So here I'm just showing what a scarce state looks like. Again, the modulus of the amplitude and a close by non-scarce state, right? So you take almost the same energy, like within 0.1% of the energy, and you see that as a non-scarce state, you immediately have contribution from all possible basis states, right? Whereas in the scarce states, you only have very well determined contributions, right? Right. So I have already explained this order by, motivated a bit this order by disorder. So, right. So there are different possibilities that can come up. So the ones that I've explained to you are the simple ones, and the one that I'll continue in that theme, that the O kinetic is 0 and O potential is labeled by an integer number, right? And so what are these states and how do you end up counting them, right? So in the quantum diamond model, it turns out that you can understand these states in a very simple way. So one of these scarce states look like this. It's just a combination of 4 Fock states, right? So what are you looking at? Once again, it's a collection of all these flux states, and those states which are so the states which are blue are the ones that are flippable. So notice that this is flippable in an anti-clockwise fashion, it's flippable in a clockwise fashion, right? And this pattern gets reversed when you go over here. All the rest of the plaquettes are non-flippable. So if you make entanglement cuts either along the the horizontal or the vertical, if you make entangle cuts along the horizontal line, you're going to get 0 entanglement. Along the vertical cut, you're going to get 2 log 2. This already tells you that there's a singlet structure involved in these constructions, and indeed it turns out that it's so. This particular state, right? This particular full state, which is, let me just show you, this was this combination C1 minus C2 minus C3 plus C4 can actually be written as a tensor product of L1 and L2 if you make the cut along this line. And this is what we ended up calling Legos. And you can these are we call Lego scars, and this is what we call Lego pieces, right? So why are the Lego pieces? So you have Lx equal to 6. In this case, you can simply break the lattice into 3 and 2 blocks, right? 3 and 3. And in the lower block, for example, you identify an active zone and a dead zone. Dead zones have fluxes arranged in such a way that you can never flip them. That's why they're dead. Whereas active zones have 2 such plaquettes which can be flipped. So this is an anti-clockwise, clockwise, right? Red, blue.
Why we can't flip the fluxes?
Because if you look at one of these states, right, you see that this is up.
Because of boundary conditions.
Not for it's because the Hamiltonian has an up S plus S plus S minus S minus. Right. So the Hamiltonian the flux flipping term, right, has this structure, which is this.
Because of the particular configuration of speed.
Right. This you cannot, because you cannot. So if you see, this is already up, flux half.
Yeah.
Up. This is also up. So to flip this, I would need a term which is like S minus, S minus, S minus, S plus. But Hamiltonian doesn't have this term. Hamiltonian has an S plus, S plus.
Okay, within the Hamiltonian fluctuation.
Yeah, within Hamiltonian, you cannot flip. Of course, you could add such terms, but those terms will break gauge invariance. So that's the part. You restrict gauge invariance and you do this, and you cannot flip any of them, but you can flip these. Right? But yeah.
So between C1, C2, C3, C4, you always flip 2 of the.
Exactly. So you can think of this as spin up, spin down, minus spin down, spin up. Think of it as a singlet.
So the clockwise and anti-clockwise moves with the other.
Yes, right. So it's really like, I have this Lego and I have these things dashed, right? Because I don't know what the values are. So I need to fit in something over here, just as the Lego pieces you have, right? And you fit in this with L2. So you have to make sure. So whenever you're joining the Legos, you have to make sure that the Gauss law is satisfied. That's the that's the thing. So as long as the Gauss law is satisfied, you can join Legos together. And this is exactly what this is. So if you write, you can write this IQMDS as a tensor product L1 cross L2, where L1 and L2 are these pieces, right? And you can go ahead and play this Lego game. So it turns out that we found that there's not two, but more than several kinds of Lego pieces you can find out. So this was a more complicated example at 1, 2, 3, 4, 5, 6, 7, 8, Lx equal to 8, right? And you have a bunch of these Lego pieces. So of course, the simplest one are singlets, but then quickly you go into states where you have a, anti-clockwise, clockwise, anti-clockwise pattern which goes around. Right? So immediately when you know that there are more than one Legos which are available to construct psi QMBS, you can make this argument that you take a ladder which is Lx Ly equal to 4, but immediately you have more than one local pieces to fit, right? And therefore you can very simply argue that the number of scaling, number of scars you can construct are exponential in the thermodynamic, right? So this is also why I said e to the v. Right? So one can play this, I think, with bigger ladders. So what happens in the quantum link model? So the quantum link model scars had kind of defeated us for quite a while until we realized that you can also give such a description for some of the scars in the quantum link model. So where Gauss law acting on psi is 0, you can construct these as short singlet representations. So instead of now having Legos which were singlets which were like 4 lattice spacings apart, you look at the diagonal coverings of the Legos, right? And this this plaquette, these black dots joined with red lines, is a shorthand for writing this as blue red minus red blue. And again, you can take take your lattice now in Lx and Ly as big as you want them, and you can start asking how many scars that I can find out, and that answer is that it's 2 to the power Lx by 2 plus 2 to the power Ly by 2 plus a constant, which is order 1. So the number is exponential, but it's exponential in the linear dimension. At least this is what we find. But what I have to emphasize is that this is only a subset of the total scars. There are more complex scars which we cannot represent. And that's why I was telling some of you that it'll be interesting to test the scar finder and see if there are other scars you can find. Right? And also for some of the scars, we have a precise understanding about what the structure is. We can write it down in an analytic fashion, and that looks fine. Right. So so we also observe like anomalous thermalization with some of these systems, which means that if you take a state which has a big overlap with the scars, it will, in the very large time limit, it will go to a different value of a correlation function than a one which has full overlap with an ETH spectrum, let's say. And I think this is at the point whether either I stop or if you want.
I think it might be good to kind of wrap up now, and
Yes.
we can go through this after the official.
Absolutely. Yeah. So right. So right. The other thing what we did was that we looked at the effect of disorder on the system. So let me not go through all the details. I will just simply mention that this is a study of disorder where you say that I'm going to restrict myself in a Gauss law sector. So I impose my GL equal to 0. So this is my sector, 0 winding sectors. And all I do is that I make the coupling lambda random. Whatever I had was uniform coupling, I just make it disordered by saying that I have an alpha and R box. And R box is just a random number between -half and +half. And alpha is a dimensionless disorder strength, which you can increase. If alpha equal to 0, this is the usual quantum link model. If alpha equal to infinite, this is the limit of infinite bond disorder. And I will stop just by telling you the key findings of what we find is that we do find we kind of constructed an estimator to look for the MBL versus the ETH phase. And what we find is that in one dimension, there are signs of an MBL phase, but even if MBL exists, it's a strongly fluctuating MBL. It's like the order parameter we find has significant probability, the probability distribution goes far away from just the MBL point. For So you see, even at alpha equal to 100, we have to take that. Our maximal lattice size is of the order of 14 cross 2, so it's 56 panes, but we have to take alpha to very, very high values even to see this. For Ly equal to 4, which are wider ladders, the alpha C can be very, very large, and we just conclude that MBL is possibly not stable, if it at all exists. Yeah. So yeah, I think we can go through this in detail if you're interested. There are some interesting oscillations that one sees, but so I think this is the story in the full pure gauge theory. There are also various things that one can do. Some of the work we had previously with Zlatko involved one-dimensional model with matter fields, but it's also interesting to ask the same questions in 2 dimensions. One has to come up with a proper numerical algorithm to study for some such stuff. There are some stuff we've looked at in 3 dimensions, which we call geometric fragmentations, but yeah, so there are more and more increasing examples where we see deviations from ETH and the call for interdisciplinary research across different communities. So thank you for your questions and attention.
It's interesting, you have this scar state that actually correspond to, you have this wildly fluctuating gains degrees of freedom.
Yeah.
But then you have very specific kind of excitation, so we call them, or
Yeah.
that you can
Right.
present